Hello everyone. Our topic for advanced algorithms, design and analysis, internal assessment tools, Floyd-Warshall algorithm or the shortest path. Our team comprises of Rushabh Gandhi, roll number 1911012, Kritarth Jain, roll number 1911020, Nayan Mandliya, 1911027, Hussein Motiwala, 1911031, and myself, Manan Pandya, 1911033. The contents that we are going to cover today are introduction, need of the algorithm, features, Floyd-Warshall algorithm, complexity analysis, comparison, advantages and disadvantages, applications, and conclusions, followed by implementation. Introduction. So the problem is to find the shortest distance between every pair of vertices in a edge-weighted directed graph. It is used for solving all pairs of shortest path problems. It compares many possible paths to the graph between each pair of vertices, and it follows dynamic programming approach to find the shortest path. The following part is going to be done by my friend Rushabh Gandhi.
So coming to the need of the algorithm, the Floyd-Warshall algorithm is a complete solution. It provides a complete solution for finding the shortest path. The Floyd-Warshall algorithm also handles negative weight. So unlike the Dijkstra's algorithm, the Floyd-Warshall algorithm can handle negative edges in the graph. The Floyd-Warshall algorithm is an efficient way to find the shortest path between all the pairs of the vertices in the graph. The algorithm can also be used to find transitive closure of the directed graph. Now coming to the next part, which is the features of the algorithm. So it works on both directed and undirected graph with positive or negative edges, negative edge weights. It is a centralized algorithm, meaning it requires a complete knowledge of graph to work efficiently. It can be used to detect negative cycles in a graph. It is based on dynamic programming principles and uses memoization to improve its efficiency. It is a good choice when the graph is small and the distance matrix needs to be computed only once. Now the further part will be taken by Nayan.
So let's move on to the algorithm. As seen on the slide, the Floyd-Warshall algorithm is on the left and the path reconstruction algorithm is on the right. Mainly the Floyd-Warshall algorithm was meant to be created algorithm. As seen from the pseudocode on the left, we are initializing two matrices of b square dimension, where b is the number of vertices in the graph. One will be storing the minimum distances and initialized to infinity, and other will be storing the path, which is initialized to null. The first two loops given in the algorithm are just as the initialization steps, where we are initializing our distance matrix to the original graph and making the distance from vertex to itself as 0, and the path will be stored in the pre matrix. So the Floyd-Warshall algorithm can be simply given as relaxing the edges by considering all the vertices in between one by one, and then increasing the number of vertices in between for relaxation. So the main four loops are doing that only. The if condition given in the main for loop is the relaxation, where the edge will be relaxed if there is some alternative path with minimum distance possible from vertex I to j. So this was all about the Floyd-Warshall algorithm. Now let's move on to the algorithm which is on the right, which is useful for path reconstruction. So basically we are constructing the path in the backwards direction. So first, the path reconstruction algorithm will take two parameters, the starting vertex and the ending vertex, and we will traverse the pre matrix which was created from the Floyd-Warshall algorithm in the manner such that the initial vertex and the final vertex are the same, and we will append all the data into a path which will store the path that is actual from vertex u to vertex v. So this was all about the algorithms. Let's move on to the complexity analysis of Floyd-Warshall algorithm. Yeah. So as seen from the algorithm, there are three for loops traversing all the vertices one by one. So it is obvious that time complexity is v cube, where v is the number of vertices in the graph, and also we are storing the distance matrix as we are storing the distances between two vertices in a form of a matrix, which is of dimension v square. Hence, the auxiliary space complexity or the auxiliary space required for the algorithm is v square. So now let's move on to the next part. So as we know, there are many path construction or path tracing algorithms which are used in the industries nowadays. All of them have their different advantages and disadvantages. So we have created a graph where we are comparing the percentage usage of each algorithm in the real world. So as seen from this bar graph, it is obvious that the Dijkstra's algorithm is mainly used in the real world due to its easiest implementation and less time complexity and space complexity. The next algorithm which is mainly used in the real world is the Floyd-Warshall algorithm, which is our topic. The Floyd-Warshall algorithm has many advantages over the Dijkstra's algorithm, like the handling of the negative edges. Hence, it is the second algorithm which has been mainly used in the real world. So now move on to the advantages and the disadvantages, which will be explained by my teammate Hussein Motiwala.
Now let's see some of the disadvantages and advantages of the Floyd-Warshall algorithm. So firstly, the Floyd-Warshall algorithm can handle both directed as well as undirected graphs. Then one of the main advantages of this algorithm over other algorithms is that it can handle negative edge weights and can detect negative cycles as well. And it's a very simple algorithm and a simple algorithm to understand and implement. Now for the disadvantages part, actually this algorithm requires a lot of memory to store the distance matrix. So this algorithm is not a recommended choice when the size of the graph is very large. This same problem occurs in time complexity as well. This algorithm, as the time complexity is the power of n cube, so the issue is that when the graph size is very large, the number of edges and vertices are very huge. This algorithm takes a lot of time to compute the answer. Although Floyd-Warshall algorithm can handle negative edges and detect the negative cycles, if the graph consists a negative cycle, the algorithm does not work and we do not get the correct answer. Moving forward, let's see some of the applications of Floyd-Warshall algorithm. Floyd-Warshall algorithm can be used in image processing for identifying connected regions and then actually computing the shortest path distance between those regions and subregions. It can also be used in molecular biology to find the shortest path between 2 points of complex protein interactions. It can also be used in computer graphics. Then it is also used in transportation networks such as roads and railways to find the shortest distance between the two locations. And applications of this can be seen in mapping applications like Google Maps, etc. Now let's conclude by seeing over the important points of the Floyd-Warshall algorithm. So basically, Floyd-Warshall algorithm is a powerful algorithm whose main purpose is to find the shortest path between all the pairs in a graph. Basically, its main advantage is the ability to handle the negative edges. So therefore, this makes it suitable for a wide range of applications. Now, due to the time complexity of this algorithm, it is not suitable for large graphs. So this limits its application only to graphs or problems which have a smaller number of edges and vertices. It is not efficient as well when the graph is sparse. And Floyd-Warshall algorithm is actually a very valuable tool in different areas such as network routing, image processing, bioinformatics, and many others. So now, after understanding and getting a gist of the Floyd-Warshall algorithm, let's move on to the implementation, which will be explained by my friend Kritarth.
So now we move to the implementation of the Floyd-Warshall algorithm. We have imported libraries like Pandas, NetworkX, and Matplotlib for displaying the results. This is the create graph function which will be used to display the graph from the adjacency matrix. We have used the adjacency matrix approach for solving the Floyd-Warshall algorithm. We take the number of vertices as input and also the adjacency matrix. We take dash as infinity wherever the distances are not present. Then we display the initial graph using the create graph method made using the NetworkX function library. Then we convert the dash values to float infinity for simplifying the calculations. Then we move on to the main function of the Floyd-Warshall algorithm. Here we relax all the edges, all the shortest path pairs that are going through the particular K. This is done for v iterations. And finally, the distance and the next matrices are updated. Next up is the print graph function, wherein the distance and the next matrices are used, and they are used to calculate the shortest path between all the pairs. This is displayed using the pandas library in a tabular format. Firstly, we initialize the next matrix with all empty values and only the edge values with the destination of the vertex. Then we initialize the distance matrix as a hard copy of the adjacency matrix. We then run the Floyd-Warshall and the print path functions on it. And finally, we print the final graph and also the final adjacency matrix. So as you can see in the output, we first accept the number of vertices and the adjacency graph with dash for infinity values. The graph is then drawn using the NetworkX library. Then since we have 4 vertices, there are 4 iterations. In iteration 0, there is no relaxation of edges. In iteration 1, there is a relaxation using root 0 to 2 through 1, as you can see. And in iteration 2, there are 2 relaxations. And similarly, in iteration 3, there are no relaxations, as iteration 3 is a separated node and no other node is connected to the vertex 3. This is the final summary of the results of the Floyd-Warshall algorithm. These are the all pair shortest paths along with their distances and their paths. Finally, the final adjacency matrix of the shortest pairwise paths are visible, and also the graph is shown using the NetworkX library. Thank you.